Now, this is a calculation in which computing it numerically versus computing it using the Fourier transform, where maybe of comparable level of complexity. Now, when you have very large sequences and you have to do this computation, you will find that the computation using the discrete-time Fourier transform is very, very simple, because you can write a simple program to do these polynomial multiplications, and polynomial multiplications will polynomial multiplication will give the output in terms of that. So multiplication generally is a simpler operation than convolution. So again, in one case it is convolution of two sequences, other case it's a multiplication of polynomials. It turns out to be that the multiplication of polynomials will give you a lot of advantages. Okay, let us continue in our discussion of our examples that we are currently looking at. Okay, this is a good point for us to introduce the concept of ideal filters. Ideal filters. So far we have introduced an ideal low pass filter. Ideal low pass filter is a filter which has a pass band, or which allows all frequencies between minus omega c to omega c, and has had a height of 1. This is an ideal low pass filter. We would like to be able to utilize our understanding of filters and the DTFT properties to see how these filters will affect our the output of the signal. So an ideal high pass filter, is one where you can think of just like the low pass filter centered around omega equal to 0, you have the same type of filter, but it is centered around omega equal to pi. Okay, so it has a pass band which is centered around pi. You can think of this as pi plus omega c, this frequency as pi minus omega c. So you would have to look at the corresponding frequency on the negative side. You will have a pass band that will also be here. So this is minus pi, and you will get okay. So this is 2 pi. So see the difference between a high pass filter and a low pass filter. Now we have two more filters which are useful for us in different signal processing applications. One is called a band pass filter. So between the low frequency, which is omega equal to 0, and the high frequency, which is omega equal to pi, this filter will pass some frequencies in this range. Okay, maybe we call that as omega A and omega B. And similarly, it will be passing these frequencies from minus omega A to minus omega B, and this is the height of pi. So this is called a band pass filter. It passes a band of frequencies in between the lowest frequency and the highest frequency. Band pass filter. Okay, if omega A becomes 0, then this band pass filter becomes a low pass filter. On the other hand, omega is not equal to 0, omega A not equal to 0, but omega B becomes equal to pi, then this band pass filter becomes a high pass filter. So again, think of it as somewhere omega and omega B are in the range from 0 to pi. And just like you have a band pass filter, we have another very interesting filter, which is what is called a band stop filter. Let us say we take the same two frequencies, the filter does not allow the signals between omega A and omega B to pass, but allows all other frequencies to pass. Okay. Okay. So I hope you have a feel for this is a band stop filter. Band stop filter. Okay. So now I have input signal which goes from minus pi to pi. Minus pi to pi has a height of 1. This is x e of j omega. Now, I want to find out what happens when this signal passes through each of these filters. Okay, so what I would have to calculate if I were to doing it in the time domain. So I will say that, okay, compute the inverse Fourier transform of this, and this is going to be a high pass filter, HP of n. This is going to be H band pass of n. This is going to be H BS band stop of n. Okay, and the corresponding time domain sequences are going to be x1 of x of n, x of n convolved with H low pass of n, that will be the first filter. The second one will be x of n convolved with HP of n. Third one will be x of n convolved with H band pass filter, HBP of n, and x of n will, this one was going to be H band stop of n. Now, computing this in the time domain, of course, is possible and can be done. We can get the, just like we got the low pass filters time domain impulse response, we can calculate. Inverse Fourier transform is quite easy in all of these examples. So, not a problem. We can actually get expressions for that. But on the other hand, if you were to apply the convolution property says it is multiplication in the frequency domain. Right. So, the multiplication part, so I can tell you that rather than compute in the time domain where I will not get much intuition as to what is happening, what sort of changes are happening to my signal, I can give you the following response very, very quickly. Okay, multiply by the low pass filter from minus omega c to omega c, height equal to 1. That is the output of the low pass filter. Output of the high pass filter. Okay. This is going to be from up to pi, right? Remember, this is pi. This is pi minus omega c. Similarly, on the other end, I will see the tail of the response. This is pi minus pi plus omega c. Okay. Remember, this signal is periodic. Right, and in the context of a high pass filter, notice that beyond pi also will be there. So, you can say that this is the next copy of the signal. Okay, that will also be visible in the sketch that we are doing. We can also show that this will be the response that, so basically the tail part of the spectrum is what the high pass filter is capturing. Now, let us go to the band pass filter. The band pass filter captures the portion of the signal in between omega A and omega B. Similarly, you get the corresponding portion of the spectrum minus omega A minus omega B. That is the band pass filter. Then finally, the band stop filter, very interesting. It will capture the value from up to the omega A, and then it will stop some of the frequencies, and then it will get you the tail of the rest. So, basically one portion of the signal has been stopped. So, this is the output of XBP E of j omega. This is XBS of j omega, band stop. XBS E of j omega. This is XHP E of j omega, and this of course is XLP E of j omega. I hope you are comfortable with this. This is very useful for us when we start designing filters, because you must have in your mind what is the behavior of the filter and how to specify the filter. And this is a good starting point if you have a understanding of how these filters will impact your signal, what modifications you want to do to your signal, and therefore which filter should you be using, and accordingly you can write down the specifications. So, what we have used here is the property of convolution, right? That is what we have used. So, this is an application of the property of convolution of the DTFT. Property of convolution has been very helpful for us to understand what is the implication of the filters that we are looking at.